Hello, welcome to another module in this massive open online course on estimation for wireless communications. And so far what we have looked at the estimation in a typical wireless sensor network considering n observations y1, y2, yn of a parameter h in the presence of noise, that is considering noisy observations y1, y2, yn when the noise samples are IID Gaussian, that is independent identically distributed Gaussian random variables. We have said that the estimate is given, the maximum likelihood estimate is given by the sample mean, which is both unbiased and has a variance of sigma square by n. Now, one thing that we have done so far is we have looked at the estimation of real parameters, which is going to be something which we are going to keep looking at in the subsequent modules also. But of course, now this can also be extended to the estimation of complex parameters. So, I am going to talk about the estimation of complex parameters, that is how to extend the results complex parameters. Yeah. So, we have looked so far a case where h is a real parameter. Implicitly, we have looked at the scenario where h is a real number. Now, one can also look at the estimation of a complex number, or basically where the parameter that is being estimated is a complex parameter. For instance, I can talk about h which is complex, which is hr plus jhi. This is basically your real part of h, and this is the imaginary part as a result of which this h is complex. So, I have h equals hr plus j times hi, where hr is the real part, hi is the imaginary part. This is a complex parameter. So, this h is basically known as your complex parameter. Yeah. So, now where does this arise, the estimation of complex parameters? That is also important. It arises in several scenarios. For instance, in the estimation of a channel in wireless communication system, the channel can be modeled as a complex baseband channel coefficient. For instance, in the context of wireless communication, in a wireless communication system, this channel H is a complex, the complex baseband the channel H is a complex baseband channel coefficient. Therefore, in such a scenario one needs to estimate a complex parameter, which is the channel coefficient. And we are going, since this is a course on estimation for wireless communication, we are frequently going to talk about the estimation of complex parameters as well. Now, the same theory that we have developed so far for the estimation of a real parameter can be extended in a very straightforward fashion to the estimation of a complex parameter, and that is what I am going to illustrate now. So, let us again consider the noisy observation model for the estimation of a complex parameter. So, let us say I have my noisy observation model. Remember, the noisy observation model is yk equals h plus vk, where h is the parameter, v is the noise, and y is the observation. Now, one can extend this to a complex parameter. So, basically your observation is complex yrk, that is the real part, that is yrk plus j times yik equals, this equals the complex parameter hr plus j times hi plus the noise which is also complex, which is Vr k plus j times Vik. So, this is your complex noise. So, this is basically your complex noise, this is your complex parameter, this is the complex observation. This is the complex observation. So, what we have, see, remember previously in the noisy observation model, we have the observation equals parameter plus noise. Now, all we are saying is everything is complex. So, we have complex observation is basically equals your complex parameter plus the complex noise. Now, what we have to do is very straightforward. We can split it into two parts, one for the real part, one for the imaginary part. So, I can split the complex parameter as two parts, one is HR which is the real part, one is HI which is the imaginary part, and basically the estimation problem can be split into two parts, one for the estimation of the real part, one for the estimation of the complex part. Therefore, I can write this problem now as basically if I split it into two parts, split the estimation problem into two parts. One is if I look at the real part, I have the real part of the observation is equal to the real part of the parameter plus the real part of the noise. Therefore, now the real problem will become, if we call this as the problem estimation problem for the real part, I have, what do I have? I have y r of 1 equals h plus v r of 1, y r of 2 equals h plus v r of 2, so on, y r of n equals h plus v r of n, where these noise samples v1, v2, where these noise samples v1, v2, vn, these are IID Gaussian, these are IID Gaussian, these are the real part of the observations, or these are the real part of the observations, these are the observations corresponding to the real part, or these are the real part of your observations y1, y2 up to yn, h is the real part of the parameter. Now, if you look at this, this is similar, this has reduced back to the estimation of the real parameter hr. For instance, let me, I am sorry, I have to write here hr, which is the real parameter. So, therefore, what I basically have is basically hr or the estimate of the real part hr equals the sample mean of the real part of the observations, that is k equal to 1 to n yr of k. So, therefore, basically what I have is I have the estimate of the, this is hr hat, which is the estimate of the, this is the estimate of the real part. What is this? This is your estimate of the, this is the estimate of the real part. Now similarly, I can develop a similar optimization problem for the imaginary part, that is, if I look at the imaginary part of the parameter, that is hi, I can look at the imaginary parts of the observations and I can develop a similar estimation problem for the imaginary component of the parameter. Again, that can be written as, now if I look at the imaginary part, I can write this as basically your yi of 1, the imaginary part of the observations is hi plus vi of 1, yi of 2 equals hi plus vi of 2, so on and so forth, yi of n equals hi plus vi of n. Now once again we have reduced this back to estimation of a real parameter. What is the real parameter? That is hi. Remember, hi is real, that is h equals hr plus j hi. Hi represents the imaginary part of the parameter h, but hi is real, right. So now we have again reduced it to the estimation of another real parameter, that is hi. Again, if these noise samples vi1, vi2 up to vin are IID Gaussian, then again the estimate of this parameter hi is given by the sample mean of the imaginary parts of the observation. So basically, if these are Gaussian, again once again, if these noise samples, these are Gaussian, if these are Gaussian IID, now these of course these are the imaginary part of the observations, these are the imaginary parts of the observations, then what am I going to have? The estimate of the imaginary part hi hat equals 1 over n summation k equals 1 to n, the sample mean of the imaginary parts, that is hi equals sample mean of yi1, yi2 up to yik. So hi hat, this is the, what is this? This is the estimate of the imaginary part, this is the estimate of imaginary part of h. And further, now how to get the estimate of the parameter h? Simply the estimate of the real part plus j times the estimate of the imaginary part. Therefore, the estimate of the complex parameter h hat equals, that is also very simple, naturally hr hat plus j times hi hat. So this is, what is this? This is estimate of real part this is estimate of imaginary part this is the estimate of the imaginary part, and this is the estimate of your complex parameter. This is the estimate of the complex parameter. So the estimate of the complex parameter h hat is estimate of the real part hr, that is hr hat plus j times hi hat, where hi hat is the estimate of the imaginary part. Now one important property that will help signify the behavior and properties of this ML estimate significantly is as follows. That is the property of the noise samples, which we have not discussed so far, which is the property of Vk, which is the complex noise. Remember the complex noise Vk, we have said Vk equals the complex noise which is VRK plus J times VIK. So, this is your complex noise, this is the real part of the complex noise and this is the imaginary part. Now, what we are going to assume is that VRK and VIK are IID Gaussian. That is, what does that mean? We are going to assume VRK is Gaussian mean 0, variance sigma square by 2, that is half sigma square. Further, we are also going to assume that VIK is Gaussian with mean 0 and variance sigma square by 2. So, what are we assuming? We are assuming that, well, first we have said this Vk is complex noise, which can be written as VRK plus J times VIK. VR is the real part, VRK is the real component, VIK is the imaginary component. We are assuming that VRK and VIK are IID Gaussian, that is both VRK, that is VRK is Gaussian with mean equal to 0 and variance sigma square divided by 2. VIK is also Gaussian with mean 0 and variance sigma square by 2. Further, both of these are independent, which means they are also uncorrelated as well. This is Gaussian because independence means uncorrelated, which means expected value of VRK times VIK equals expected value of VRK times expected value of VIK. Now, both of these are 0, both of these are equal to, this is equal to 0, this is equal to 0, which means expected value of VRK times VIK equal to 0. So, these two components, the real part and the imaginary part, are identical, that is both are mean 0, variance sigma square by 2, and further they are independent, that is the expected value, which means the expected value of the real part times the imaginary part is equal to 0. Such a noise, so both real and imaginary components are identical, Gaussian, and both the real and imaginary parts are independent. Such a noise is known as a complex Gaussian noise. Further, it is a zero mean symmetric complex Gaussian noise. So, let me elaborate on that fact a little bit more. Vk is known as the zero mean symmetric complex Gaussian noise, and this is the most important frequent assumption, which stands for zero mean symmetric. Each of these words has a meaning: complex Gaussian. This is an important property of complex noise, that is Vk is known as symmetric zero mean complex Gaussian noise. What is the meaning of symmetric? It's symmetric because the real part and the imaginary part are basically symmetric, that is they are identical, they are both zero mean and variance sigma square divided by 2. They are symmetric, zero mean, yeah, that is both the components, the real component and imaginary component have zero mean, complex, that is its noise Vk is complex in nature, Gaussian, both the components, the real part and imaginary part are Gaussian, and this is noise. Therefore, this is zero mean symmetric complex Gaussian noise, which is basically, is to summarize, Vrk, that is the real component, your VRK and VIK are both 0 mean variance sigma square by 2, VRK comma VIK are independent. That is, both of these are basically identical Gaussian. Both of these are basically identical Gaussian and both of these are independent, and this is basically known as symmetric complex Gaussian noise. In that case, now you can say that basically expected Vk, the complex noise Vk is expected Vrk plus j times expected Vik, which is basically 0 plus j times 0, which is equal to 0, that is Vk is also 0 mean. Further, the variance of the power of the complex noise in noise expected magnitude Vk square is expected magnitude Vrk square plus expected magnitude Vik whole square, which is equal to sigma square by 2 plus sigma square by 2, which is equal to sigma square. So, expected Vk, the complex noise Vk is 0 mean, the magnitude Vk square, expected value, the variance of the complex noise is sigma square, in which the real component has half the power, the imaginary component has half the power. Both of these are Gaussian, 0 mean, and they are independent. That is the expected value of Vik times Vrk is 0, since that is they are uncorrelated. Since they are Gaussian, so automatically means that they are independent. That is, both the components are basically symmetric, Gaussian, symmetric, independent and identical, and such a noise is known as 0 mean complex, that is 0 mean symmetric complex Gaussian noise, because the noise is complex in nature, therefore naturally it is complex Gaussian. Now, with this property, the estimate, the ML estimate, the behavior of the ML estimate can be simplified further. Now, if you look at the ML estimate, now remember we have said HR hat equals 1 over n, the sample mean of the real part of the observations, that is k equal to 1 to n y of the real part k. Now, of course, I can simplify this as follows. I can simplify this if I substitute for every, remember we did this already when we looked at the behavior of the maximum likelihood estimate. There is a real part of k is HR plus j times Vr of k. So, therefore, if I substitute this for Yr of k, that is I will get H hat, the real part is basically H, that is the real part of the parameter plus the sample mean of the real components of the noise, that is k equal to 1 to n Vr of k, and therefore, once again we can show that expected value of HR hat equals HR, that is the real part, the estimate of the real part is unbiased. The variance of the real part, expected value of HR hat minus HR whole square, is the variance of 1 by n times the variance of each noise component, but the variance of each noise component is sigma square by 2. So, this becomes sigma square divided by 2n. So, the variance of the real part, that is the variance, that is the mean squared error, that is the variance of the real part of the error, the variance of the real estimate variance of estimate of real part is sigma square divided by 2n. Further again, now we can extend this again to the imaginary part, that is hi hat. Remember, I wrote this as 1 over n, the sample mean of the imaginary part of the observations, that is k equal to 1 to n y of imaginary part of the kth observation yi of k, which now you can simplify as hi plus 1 over n summation k equal to 1 to n vi of k, and therefore it follows that the imaginary part is also unbiased. The estimate of the imaginary part, that is expected value of hi hat equals hi, and further the variance of the real imaginary part, the estimate of the imaginary part, expected value magnitude of hi hat minus hi whole square equals sigma square divided by 2n. And now if you look at, it is important at this point to look at the errors. Now look at the errors, hr hat minus hr, that is the error in the real part, hr hat minus hr, let us call this as wr, that is the estimate in the error in the real part, that is 1 over n summation k equals 1 to n vr of k, and the estimate of the error in the imaginary part, that is hi hat minus hi, if I call this as wi, that is the error in the imaginary part, that is equal to 1 over n summation k equals 1 to n vi of k. Now look at the interesting property, we have the different Vik and Vrk, because we are assuming 0 means symmetric complex Gaussian noise, Vik and Vrk, the real and imaginary parts of noise Vk are independent, and further these different complex noise samples are independent anyway. Therefore, what we have is basically all these noise components, that is Vr1, Vr2 up to Vrn, Vi1, Vi2 up to Vin are independent, are all mutually independent, in fact independent identical Gaussian. So now if you look at all the noise samples taken in total, that is we have Vr1, Vr2 up to Vrn, we have Vi1, Vi2 up to Vn, all of these are in fact IID Gaussian, these are IID Gaussian, all of these are IID Gaussian, mean 0, variance sigma square by 2, and therefore now if you look at the correlation between the real and imaginary, the errors on the real and imaginary parts, that are Wr and Wi, Wr depends only on the real components of the noise, Wi depends only on the imaginary components of the noise, therefore the correlation between the errors of the real part and the imaginary part is 0, and that is an important property, that is expected value of Wr times Wi equals 0. Further, these are Gaussian, which means it also follows that Wr comma Wi are independent, and this is a very subtle property, but a very important property, which says that if you look at basically the estimate of the real part and the estimate of the imaginary part separately, once you have decoupled this problem into the estimation of the real part and the estimation of the imaginary part, the estimate of the real part has a variance which is sigma square by 2n, the estimate of the imaginary part has a variance which is sigma square by 2n. More importantly, it says that if you look at the error in the estimation of the real part and the error in the estimation of the real imaginary part, these two estimation errors are basically uncorrelated, and now by virtue of, because the noise is Gaussian, they are also basically independent. although it is not generally true that they are always independent, generally it is true that they are uncorrelated. If you have symmetric noise, they are uncorrelated, but here specifically we have an example where the noise samples are Gaussian, so it also follows that basically they are independent. So, the estimation errors in the real part and the imaginary part of the parameter are independent. So, these are WRWI, remember these are, this says these are the estimation errors, these are estimation errors, that is estimation errors the estimation errors of the real and imaginary parts are basically, the estimation errors of the real and imaginary parts are basically independent, and that is an important property. That is, I can treat this as basically the estimation of the real part and the estimation of the imaginary part, and the estimation of the real and imaginary parts are independent. Now, if I look at the estimation error in the complex parameter as a whole, that is, remember, if I look at expected value of, remember we already said that if I look at the expected value of the estimate of the complex parameter, that is the expected value of estimate of HR hat plus J HI hat, which is the expected value of estimate of HR hat plus J times the expected value of estimate of HI hat. Of course, this is equal to HR plus J times HI. So, therefore, the estimate of the complex parameter is unbiased. Therefore, estimate of the complex parameter equals H hat equals H, which is the complex parameter, that is equal to HR plus JHI. So, this estimate is an unbiased estimate. So, this is basically unbiased. The maximum likelihood estimate of the complex parameter is unbiased. The estimate of the complex parameter is unbiased. So, this is the estimate of the complex parameter . This is unbiased. Further, if you look at the variance in the estimate of the complex parameter, that is expected value of magnitude of H hat minus H whole square, that is basically expected value of magnitude of H hat real minus H hat H real whole square plus expected value of the variance of the imaginary part, that is H hat I minus H I whole square. Now, each of these components is sigma square by 2n, as we have shown earlier. This is sigma square by 2n, this is sigma square by 2n. So, net we have sigma square divided by n, net we have sigma square divided by n. And therefore, what we have seen is the following interesting thing, that is the real part has a variance that is given by sigma square divided by 2n, the imaginary part has a variance that is given by sigma square by 2n, the error variance of the total estimation of the complex parameter is sigma square by n. Another way of stating is as follows: if I have a complex parameter h and if I estimate it, I can use the same maximum likelihood estimator that I have derived for the estimation of the real parameter, correct. So, I have the same maximum likelihood estimator, that is the sample mean, yeah. And what we have shown is basically, if we assume in addition, if the noise samples are complex Gaussian, zero mean and symmetric, which means the noise samples have real and imaginary parts which are independent, complex Gaussian, identical independent Gaussian and identically distributed. In that scenario, where the complex noise is such that each the real part and imaginary part each have 0 mean and variance sigma square by 2, the error variance of in the estimate of the real part is sigma square by 2n, the error variance in the estimate of the imaginary part is sigma square by 2n, the error variance in the estimate of the entire complex parameter is sigma square by n. Or in other words, if the error variance in the estimate of the complex parameter is given by sigma square by n, the error variance in the estimate of the real part and the error variance in the estimate of the imaginary part is basically half of that. Yeah, and further it is also important to note that the estimation errors in the real part and the imaginary part are basically uncorrelated, and specifically in this case of Gaussian they are independent. Yeah, this is an important property, that the estimation errors of the real part and the imaginary part are uncorrelated or basically independent for this specific case of Gaussian. So that is how basically we can extend the same results. We are going to use this property when we talk about the estimation of complex parameter, as we have mentioned there in the example at the beginning of this module, that estimation of complex parameters arises in the context of wireless communications, where you are estimating the complex channel coefficient. So once we derive, for instance, an estimator for the real part, the same can be used to estimate the complex, to estimate a complex parameter, noting that basically the estimate in if the noise is 0 mean, complex Gaussian, symmetric, the estimates, the errors in the estimates of the real part and imaginary part are basically independent, and also basically the errors in the estimate of the real part and the imaginary part have half the variance of, half the error variance of basically the estimate of the total complex, that is the error variance in the estimate of the complex parameter. And this is an important property to keep in mind when we extend the results for the real parameters to the complex parameters. So with this insight or brief note about the estimation of complex parameters, we will stop this module. We will continue with other aspects in subsequent modules. Thank you very much.